just start working now, otherwise we won't have time. We're going to be out of oil within a few years.
Quest for fusion energy could very well be the next great American enterprise.
Natural gas is getting short, everything's getting short. Unless we can harness the power of the sun, it's going to run out eventually.
Okay, engine stop. Houston, Tranquility Base here. The Eagle has landed. That's one small step for man, one giant leap for mankind.
That was an unforgettable moment. Not just for me, Neil Armstrong, but for all of us. It was the culmination of a long and difficult effort that took the dedication of hundreds of thousands of people and cost billions of dollars. But I'm not here to tell you about that quest. I'm going to tell you about another, which may be even more difficult to achieve, but which may pay us even greater rewards if we succeed. The quest for inexhaustible supplies of cheaper, cleaner, safer energy. Fusion energy. Just imagine what that might mean. Unlimited energy, without having to stand in line for it, without having to dig up the land, pollute the air, or risk polluting the sea for it, and without ever having to negotiate with other countries for it. To achieve fusion on Earth, scientists at Lawrence Livermore National Laboratory in California are attempting no less than to recreate the extreme conditions that exist naturally in the core of the sun.
We're here at the Lawrence Livermore National Lab, talking with researchers at the National Ignition Facility about fusion ignition and the future of fusion energy.
Nuclear fusion is the last energy source that humans haven't been able to capture and hold together yet. And it's an energy source that will last us not hundreds or thousands of years, but literally millions of years. So it's the last energy source that humans ever need. The National Ignition Facility is the largest, most energetic laser in the world. It's roughly 3 football fields in size. It's 10 stories tall at the biggest and 4 stories tall through most of it. It's about 60 times bigger than the predecessor laser before it, and it's used to understand the types of physics that goes on in our nuclear weapon stockpile. So it's here to understand the physics and make sure that our weapon stockpile is safe, secure, and reliable. It also has the great benefit of doing experiments that test really energetic, high energy density is what we call it, phenomenon that exists both in astrophysical events, like when stars merge together and explode, or other types of interiors of large planets, like the interior of Jupiter or the atmosphere of Neptune. We built NIF 15 years ago. It started turning on, and we were learning from day one. So the physics that we thought we knew beforehand, we had very good predictions. But once you start to operate in a different regime, you're testing different physics. And so once we got there, we said, oh, we need to learn a little bit more about this. Kind of went backwards, understood the base physics, and then we're able to kind of progress forward. And it's just in the last 5 years that we've been able to really accelerate that through to having a place where there's no more fundamental physics left to slow us down. We're getting more energy out of these experiments than what we put in with the laser. And it's the first time in human history in a laboratory we've been able to do that. Fusion is bringing 2 smaller things and fusing it together to make something larger. In our case, we do nuclear fusion, which is taking elements of hydrogen, squeezing them together, making helium afterwards. There's a little bit more mass in the hydrogen than there is the helium. And that difference in mass is Einstein's equation, E = mc squared. So that extra mass turns into pure energy. And so we get a net output of energy in doing these fusion reactions. So there's a lot of different ways to make fusion. You can smash the particles in together, just a one beam onto another. You can have magnetic confinement fusion, which is another big approach that lots of other universities, companies, national labs are using. It's having the plasma that we have here. It's much lower density, and you hold it together with magnetic fields and try to get the fusion to happen there. In our case, we use the inertia of the fuel and the capsule that we have the fuel inside. We squeeze it together. All of that mass holds it together for a very short amount of time. So we try to get things really hot, really dense, and hold it there for long enough that the fusion reactions happen. The funding that we have is directly coming from our US government. We do work that is critical to national security and the energy mission in the larger government context. The role of Lawrence Livermore National Lab is to understand the physics. We as a national lab are not interested in commercializing anything, but we are the resource to the community and the nation to be able to have really exciting technologies that can change the world. Private investment has really accelerated over the last 5 or 6 years. There's now something like $8 billion of private money that has gone into the fusion space. So we're seeing that really take off just very recently. So that's able to fund companies. They're able to spin up very quickly, be able to test really exciting ideas that maybe we haven't been able to explore fully in publicly funded institutions. And so they're out and they're pushing the boundary, and they may be able to get to fusion energy in a more economic and faster way. But the national labs are a place where we can be the resource to those companies too. If they've got problems that are kind of too big for them to solve or too hard, then we're in a place to be able to help with that.
How do we transition this technology into a power plant?
So NIF was built as a demonstration to do the first question of, can you get more energy out than in? If we're going to take this laser today and try to convert it into a power plant, there's a lot of things that would need to change. It's a lot of the efficiencies, trying to get as much laser power delivered to the target as efficiently as possible, and then create that energy and harness the energy that's created from the fusion. So this is a 3D printed model that we use to explain how we would make choices going from today's technology to something that would be a fusion reactor. Each one of these boxes here is a laser beam by itself. It replaces one of the laser beams at NIF. And then these are the optical paths of the laser that propagates through a shield wall and then down into the reactor chamber. And this orange dot in the center is where the fusion would happen. The energy that's created in that central area is absorbed by the chamber wall here, converted into first heat and then efficient electrical energy.
How far away are we from this point right here?
So it might sound like we're really far away. We're running this facility, hundreds of times a minute, and today we only do kind of 2 experiments a day. But really, this is a Wright brothers moment where we're first able to demonstrate flight, and in just a few decades, we were able to take 747s across the Atlantic. So this is not something that's so far away. The technology has all been demonstrated at a really low level. It's just how fast can we commercialize it and get to the end goal.
The stakes are high as humanity. This is one of humanity's grand challenges, to basically unlock unlimited carbon-free energy with the fuel coming from deuterium and seawater that's naturally abundant. It's completely game-changing for humanity if we can get this working. And it really is, the when just depends on how much investment we can put in and how much progress we can make in a reasonable amount of time.
Can you talk a little bit about stockpile stewardship and what that has to do with fusion research?
Yeah, so that was the reason that NIF was funded and built in the first place. At the end of nuclear testing in the early 90s, the government decided we needed a experimental facility where we can access some of the same super high energy density pressure conditions, same ones that go on in the detonation of a nuclear device, in order to ensure the continued safety, reliability of our nuclear stockpile. And also having an experimental check on the people are understanding our design codes. They're very sophisticated. We run them on some of the biggest supercomputers of the world, but they're still not perfectly getting everything correct in 3D. We have to make some assumptions and some concessions in order to be able to make the problem tractable. So having experimental data to really confront your understanding against is where the learning happens. December 5th, 2022, it was the first time that we got out more energy from the fusion reactions than the laser energy we put into the target. And we got out 3.15 megajoules from using 2.05 megajoules of laser energy. Now, of course, was the first time in the world this has been done in a laboratory in a controlled way. And so super, super exciting to be a part of that. We've attained ignition 8 times in total over the error bars, and there were a few that got really close as well. And it's not just repeating the same exact design, same exact laser pulse. We're trying to continue to improve things to increase the gain, so get even more energy out relative to the laser energy we put in. And we've been steadily improving. We can create some of the most high energy, high pressure, high density conditions that we can make on Earth in a controlled laboratory setting. We can study some of the same physical processes that would need to be controlled to create a fusion-based power plant for fusion energy. No one said it got easy right after doing it once. These are still an incredibly complex facility that everything has to work really well every time we want to do an experiment. The targets that we are firing are some of the most pristine, perfect objects made by humankind. These capsules have to be perfectly round to within fractions of a micron. So there are all sorts of little things in the process that can just go awry a little bit, and that's enough to take us off the ignition cliff right now. We're setting the foundation, we're building up the scientific building blocks we need in order to turn this into a reality and unlock fusion energy in a power plant at some point in the future. For the good of the planet, for our ability to continue to mature technology and satisfy the needs of a growing population that's going to consume more and more energy, we kind of need this for our survival as a species.